Welcome back to part 2 of applications of powers of matrices. We were playing with the A matrix, and he was 1, 2, 3, -4. And one of the other things that we can do besides find powers of that A matrix is we can, just for fun, remember that the characteristic equation was lambda squared plus 3 lambda minus 10 equals 0. We're going to plug this A matrix into that and see what happens. And to do that, let's quickly find A squared. Okay, so we'll have 1 plus 6 is 7. 2 minus 8 is -6. 3 minus 12 is -9. And 6 plus 16 is 22. So let's see what happens if I do A squared plus 3A minus 10, but I can't just minus 10 a constant, so I have to do 10 times the identity so that I have matrix plus matrix minus matrix. So we've got 7, -6, -9, 22, plus 3 times our original A matrix is 3, 6, 9, -12, minus 10 times the identity matrix. And let's see what we get. 7 plus 3 is 10, minus 10 is 0. -6 plus 6 minus 0 is 0. -9 plus 9 minus 0 is 0. And 22 minus 12 minus 10 is 0. So that means the characteristic equation, the matrix satisfies his own characteristic equation, giving us the 0, but the 0 matrix. So let's quickly remember that matrix M was this guy, and his eigenvalues and eigenvector pairs were as follows. So let's find M to the 5th power here. So if we make a P matrix, P is equal to, and I'll just use them in the corresponding columns that they already came in. And if I do that, then my diagonal matrix will have those corresponding eigenvalues down the main diagonals, or down the main diagonal, I should say. And as we saw on the front, M to the 5th power will be D to the 5th power times P inverse. Okay, so we could find out what P inverse is. We'll probably use tech for that. And then D to the 5th power, so we would have 1, 1, 0, 0, 2, 1, 1, 0, 1. D to the 5th power, so we'll have 3 to the 5th power, 3 to the 5th power, and 6 to the 5th power. And then let's find matrix P inverse. Well, let's see, I'm going to have to type that into my calculator, so we'll pause on that for a second. Okay. Matrix P inverse was 2/3, -1/3, 1/3, 1/3, 1/3, -1/3, and then we have -2/3, 1/3, and 2/3. We could factor the 1/3 all the way out front. Okay, and then we'll have a lot simpler multiplication. Instead of having to multiply M by itself 5 times, I only have to find an inverse matrix and then multiply matrices here, which is going to be easy because it's multiplied by a diagonal matrix, and then this product times this guy, which is going to be a lot quicker computationally than having to multiply him by himself, by himself, by himself, by himself. And if we do the work on this guy, we will find out that m to the 5th power turns out to be 243, 0, 0, negative 5,022, 2754, 5022 again, negative 5022, 2511, and 5265. So that's what m to the 5th would be in a computationally easier method using the diagonal matrix and the fact that the matrix is diagonalizable. Okay, so let's keep going here. And remember that when we found matrix M to find its eigenvalues and eigenvectors, we solved our characteristic equation, or for our characteristic equation. And what I want you to do is put M into this characteristic equation everywhere there's a lambda. And since this is matrices, we'll have to throw on an I here and see what you get. So I've got matrix M in E in my calculator. So let's try it. So matrix E to the 3rd power minus, I'm getting a little bit of glare there, 12 matrix E plus 45, that should have been E squared. Good, I caught that. Insert squared plus 45 times matrix E, and then minus 54 times matrix, I need the 3 by 3 identity. And lo and behold, we get the 0 matrix, showing once again that the matrix satisfies its own characteristic equation. So m cubed minus 12m squared plus 45m minus 54 identity is the 0 matrix. So he satisfies his own characteristic equation, which is simply what we call the Cayley-Hamilton theorem, that if a matrix has a characteristic polynomial given by this guy, then if we stick the matrix into that characteristic polynomial, basically the characteristic equation, then he will be equal to 0. So what does this have to do with other applications? Many times we have a situation where the output then goes back in and gets worked on again. So sometimes a predator-prey model. So we take a look at the situation and then we come back in a year and measure the predator and prey, and then we come back in another year and measure the predator and prey. And so the output then becomes the input for the next cycle, whether it's predator-prey or population and migration. And oftentimes we can represent this by a matrix multiplication. And so we look at this as what we call a transition matrix, because it takes us from the kth step with a matrix multiplication to the k plus first step. And let's take a look at an example here. In a certain area, there are predators, we'll call them F for foxes, and prey, R for rabbits, and their growth or death rates for each species is given by this system. So for the number of foxes at the next time period, it's going to be 40% of the time of the 40% of the foxes at the previous period plus 30% of the number of rabbits at the previous period. So the foxes will grow based on how many rabbits there are to eat, and the rabbits themselves will also decrease based on the number of foxes there are. The more foxes, the fewer rabbits we'll get, but the rabbits themselves also reproduce. Okay. Let me show you an applet I found that can help us see this. Where did it go? Okay, so if we go to our home page and then click on the online resources for differential equations, one of the options is a predator-prey model. And if you click on that, it will bring up this guy right here, and it will do a simulation for us. So we can see that we've got bunnies, several bunnies around here, but we've also got some foxes going on here, and they're on a grassy field. So the bunnies are both predator and prey. They're predator to the grass, but prey to the foxes. So we'll start here and take a step or two. So you can see how the bunnies have eaten some of this and some of the grass. So the grass is going away. And then the foxes are going to get closer to the rabbits. But let's go ahead and put this in motion. Let's do a reasonable speed to start. And let me pause and show you the population graph. Ooh, let me slide this up here. And we'll resume the simulation here. So you'll see the red is the foxes, the blue is the rabbits, and the green is the grass. And as time goes on, each period, whoa, look at that. So the foxes started to grow, and in fact, and the bunnies tailed off. And so you'll see that the grass is starting to grow, and now all the rabbits have died off. So guess what's going to happen to the fox population? And the winner is the grass. So come back in the next video to find out more.